Hi, and welcome to Module 6. In this module, we present an introduction to the most important concept of all modern astronomy, spectroscopy. By analysis of the light emission from stars, we can determine the chemical composition of the universe. We investigate this atomic process and present the three basic principles laid down by Gustav Kirchhoff in 1859. Each element has a characteristic spectrum of light, its DNA fingerprint. Review this slide to learn about the two branches of spectroscopy.
We have terrestrial spectroscopy and celestial spectroscopy.
This figure indicates the gross level of identification of atoms. From left to right, salts of calcium, potassium, copper, strontium, and sodium by combustion with a Bunsen burner. EM radiation can be quantitatively analyzed with an instrument called the spectrograph. Review this slide to learn more about the spectrograph. Emission spectra is the term for the light patterns given off by terrestrial elements when volatilized and analyzed with a spectrograph. Review this slide to learn about emission spectra.
Volatility is the tendency of a substance to vaporize. At a given temperature and pressure, any substance can vaporize into a gas. By 1856, volatilization was best done by vaporizing atoms with hot gas from the newly invented Bunsen burner. In the 20th century, it was discovered that using electricity as the source to vaporize atoms to emission was much more efficient. Every atom on Earth emits a pattern of EM radiation that is unique and specific for that atom when it is raised to a temperature necessary for volatilization to occur. And we get a diffraction pattern imaging.
This demonstration will demonstrate the internal principles of spectroscopy and the spectroscope. What we see here are two machines that generate high voltage electricity. And what is in Guy Gore's hand is a tube of helium gas, and this is a tube of hydrogen gas. Of course, the gas is invisible because the atoms are way too small to be seen, just like atmospheric gas. And what I'm going to do now is I'm going to send electricity through the gas. In this case, we're sending electricity through the hydrogen, and notice that we get a pink emission from the hydrogen gas. And now here's the question. If there's nothing in that clear tube but hydrogen gas, where does the pink color come from? The pink color must be coming from the electrons that make up the atom called hydrogen, and as they are electrically excited, they glow pink. Hydrogen is the simplest element in the periodic table with one electron. Helium has two electrons, but watch, it glows a completely different color. Helium glows bright yellow. Again, where does the yellow color come from? It can only be coming from the excitation of the electrons that make up the gas. The electricity excites the electrons to an electromagnetic radiation, which equals a vibration, in this case, of very close to the red 700 nanometers and 500 nanometers in the center. But the investigation goes on. Now let's look at the tubes in the dark, and now we will add the diffraction grating mechanism, which is just a thin piece of glass with thousands of ruled parallel etched lines. And then when we put it in front of the hydrogen gas, notice that we see, notice that we see an entire set of colored lines that are being split from the hydrogen gas by this little instrument called the diffraction grating. And each of these is a distinct color. See your note set. And if we do it for the helium, watch this, okay? On the helium side, we get a beautiful yellow line emission. A couple of blues, some reds, but notice when we switch it over to hydrogen, we do not see the yellow line emission. Notice it's not there. Bright yellow line emission, no line emission. That means if I was to turn off the helium gas and ask you, class, does this gas have any helium in it? You would put your spectrograph up to it, and you would discover that you do not see the characteristic line given off by helium gas, namely the yellow electromagnetic line. And therefore, you can definitively say that this gas does not contain helium. And in fact, what we are seeing is what we call the diffraction DNA fingerprint of hydrogen gas. And again, if you look at the helium gas, you can see that it is emitting. So these parallel grooves discovered or created by Joseph Fraunhofer to break up light after Newton's discovery allows us, every single element gives off a particular set of lines which are characteristic of that element. And if you have those set of lines in an absorption spectrum from the star, you have that element. And finally, again, the diffraction grating is nothing but a very thin slice of glass with thousands of parallel straight lines etched in it that act like microprisms. Here you see the photographs of the emission spectrum from hydrogen and helium gases, respectively. If you knew nothing but that helium displays a beautiful yellow emission line at 570 nanometers, and you then look at the image in figure 11, and I ask, does that emission spectrum show the yellow line of helium? No. Notice there is no yellow line in the energized hydrogen spectrum. Therefore, you know the gas in figure 11 cannot contain helium. Welcome to atomic spectroscopy. Remember, hydrogen and helium gases are invisible in their natural state. Seriously, can you see hydrogen or helium gas? When you fill up the balloon, can you see it? No. But if we seal some gases in a tube, as we did in the previous experiment, and apply 120 volts of electricity through the gas, it glows pink and yellow. Question: in the continuous spectrum of the pink from the hydrogen gas, where does that color come from? Pause, munch, think about it. Well, evidently, the hydrogen must be giving off enormous amounts of radiation from the atoms of hydrogen themselves, because there's nothing in the sealed tubes except hydrogen gas. And they emit a dominant radiation of about 700 nanometers, a very pink-red wavelength area, which you see on the left. Let's do a second experiment. This time we seal an invisible gas tube of helium and apply 120 volts of electricity to the gas. And voila, its continuous spectrum shows golden yellow, showing that helium atoms emit a dominant radiation of about 575 nanometers, a very golden yellow wavelength area. But as my friend Dr. Quantum would say, when we apply a spectrograph and diffraction grating in the path of the continuous color spectrum, a whole new weird world of optical physics is open to us, what we call emission spectra.
Review this figure to learn about the idealized spectrograph.
Dispersion and diffraction grating separates light of different frequencies. That is the concept of the spectroscope. We see in this image the continuous spectrum of hydrogen being split into its characteristic lines and the continuous spectrum of helium being separated.
Here we see emission spectra given off by 5 different terrestrial elements when analyzed with a spectrograph.
Notice on the bottom, the wavelength scale is the visual range discovered by Newton from 700 to 400 nanometers. And notice that each element is completely individual fingerprint.
The discovery and invention of celestial or stellar spectroscopy, which is the ability to determine the chemical composition of starlight in the universe, is even more fascinating. Joseph Fraunhofer, with his newly invented diffracting grating, attached it to a telescope and discovered a new phenomenon in Newton's continuous solar spectrum. He discovered absorption spectra. Instead of a continuous band of colors, Fraunhofer's solar spectrum was crossed with hundreds of black spaces, or lines. In his first map, he counted over 574 dark lines. The scientific meaning of these dark lines was unknown. Solving the relationship between celestial absorption spectra and terrestrial emission spectra was one of the greatest achievements of 19th century astronomy.
So by replacing the eyepiece in his telescope with a diffraction grating, Fraunhofer, instead of getting the continuous spectrum discovered by Newton, saw a spectrum crossed by hundreds of dark black lines, which took 150 years worth of further work to analyze to figure out that that represents the chemical composition of stars.
Fraunhofer examined the absorption spectra of a number of stars. He found out that the spectra of Sirius and other first magnitude stars differed from our Sun and from each other, thus founding stellar spectroscopy. This is our understanding today. The black banded color image pattern given off by a star, when viewed through a diffraction grating, is called its absorption spectrum. In an absorption spectrum, a pattern of dark lines on a continuous colored background is produced when light from a hot object passes through a cooler gas. The fact that the spectra of most stars consist of dark lines on a bright background means that these stars have hot interiors surrounded by cool gases in their upper atmosphere. The dark absorption lines associated with a given element in a star occur at precisely the same wavelengths as the emission lines produced when that element is vaporized into a gas here on Earth. Both sets of lines therefore contain the same information about the composition of the gas, and so constitute a unique fingerprint for every element. Review this image to get a better understanding of diffraction grating.
This image shows you in the upper left-hand corner a star emitting light. On the left-hand side is Newton's discovery that if you put a prism into the light beam, it breaks it up into a band of colors. On the upper right-hand side is Joseph Fraunhofer's discovery that when you put a diffraction grating and look at a star, gases are absorbed in the outer shell and you get black lines. And at the bottom on the right is the emission line spectrum of atoms here on Earth. So emission lines are emitted here on Earth, and absorption lines are emitted by stars. They both represent the same thing, chemical composition of the body.
The examination of starlight with the spectroscope can provide us with 5 important facts. Review this slide to find out what those 5 facts are.
So from the light of a star, we can tell the temperature of objects in the universe, their chemical composition, the condition of matter in the stars, the magnetic field structure of celestial objects, and if the motion of the star is towards us or away from us. This shifting of the what's called the red line is Hubble's work, which we will look at in the last section of the course.
Atoms and molecules provide us three types of spectra. Review this slide to learn about what those three types are.
Okay, you got it? We're moving on.
Review this image to learn about the principle of spectra of stars.
So again, by replacing the eyepiece with a diffraction grating, the continuous spectrum is broken up with black lines, which is gases absorbed in the atmosphere of stars.
Modern spectra are usually recorded digitally and represented as plots of intensity versus wavelength. Different types of stars show different characteristic sets of absorption lines.
So here we see roughly 10 different star types listed on the left-hand side. We see on the bottom the visible wavelength, and we see the chemical element difference within these stars.
The basic principles of spectroscopy are known as Kirchhoff's laws of radiation. A solid, liquid, or dense gas excited to emit light will radiate at all wavelengths and thus produce a continuous spectrum.
Emission spectrum, continuous spectrum, absorption spectrum.
If light comprising a continuous spectrum passes through a cool, low-density gas, the result will be an absorption spectrum. A low-density gas excited to emit light will do so at specific wavelengths and thus produce an emission spectrum.
So what we see on the screen here are two nebula regions or stellar inertia regions in space. On the left-hand side, all the little dots are stars, but the pink is free hydrogen gas in space. And on the left-hand side, we see another group of stars surrounded by huge green regions of gas, which is ionized oxygen. So as these stars are in motion in the interstellar clouds, they combine and collide to produce new star bodies.
By comparing line strengths, we can measure a star's surface temperature.
So understand, by analysis of light, we are therefore able to determine the temperature of a star. So we've learned about spectra, spectroscopy, emission, and absorption spectrum, the differences between them, the principles of spectra of stars, and Kirchhoff's laws of radiation.